Let's take a look now at example 3 and continue to try to play with this idea of different units of time. Let's suppose the following scenario is the case. Let's say that I'm told that I need to take the number 1 bus to the train station. Now, of course, me being me, I misunderstand these directions and I think that I'm supposed to wait for the first bus to arrive. So I'm not looking for bus number 1, but I think, oh, it's the first bus. Well, suppose that buses arrive at a bus stop according to a Poisson process, that there's an average of about 1 bus that shows up every 15 minutes. And I'm going to be taking, the first bus that pops up. What is the probability that Kyle will have to wait, that I'm going to actually have to wait over 30 minutes for the bus to arrive? Remember, it's just an average that they show up every 15 minutes, so it could be a little bit longer, it could be a little bit less. Well, notice again in the question, I'm interested in trying to figure out a certain amount of time that I'm going to have to wait. So I can see here that maybe right off the bat, I can define my random variable, x, to represent the amount of time it takes for the next bus to arrive. Okay, so I know here that x has an exponential distribution. And I can see that in the problem, I'm told that lambda is going to be equal to 1 bus every 15 minutes. So it's lambda here is 1, and this is bus per 15 minutes. So my lambda's 1 if my time interval is 15 minutes. But the question is, what is the probability I'm going to have to wait over 30 minutes? Now again, I can deal with any amount of unit of time that I want. Here, I'm going to deal with 2 different types of units of time. I'm going to again try to think about what would be the case if I was, say, going to work in hours. And I'm also going to see what would happen here if I actually worked with this red 15 minutes that I have here. So notice that right off the bat, I'm going to go ahead and I'm going to convert my lambda over. If there was 1 bus that showed up every 15 minutes, what would you imagine lambda would be if I was going to do number of buses per hour? How do I get from 15 minutes to an hour? Well, if you're thinking multiply by 4, you'd be absolutely right. I should expect 4 buses to show up in an hour if there was 1 bus that showed up every 15 minutes. So here, I'm going to see that I'm going to kind of divvy up my page again into 2 different possible approaches. On one side, I'm going to deal with what happens if we're measuring things in 15-minute intervals. And over here, what happens if we're measuring things in an hour interval? Okay, let's see. So I'm going to go ahead and I'm going to draw out my picture on the left. Here I know that x is being measured in increments of 15 minutes. So if I have 1 on my axis, that represents 1 increment of 15 minutes. That represents a 15-minute chunk of time. 1 15-minute chunk. 2 would represent 2 15-minute chunks. 3 would represent 3 15-minute chunks. So when I draw out my distribution, and I say that I want the probability that the amount of time I have to wait is going to be over 30 minutes, I'm going to have to convert that into 15-minute chunks. How many 15-minute chunks do I have to do in order to get to 30 minutes? Well, what I'll see here is that I actually am going to have to do 2, right? 2 15-minute chunks is the same as 30 minutes. And I'm going to go over 2. Notice on the other side, I have a similar sort of conversion to do. I can go ahead and say here, if x is being measured in hours, then my distribution is going to look something like this. And if I want to do 30 minutes, how many hours is 30 minutes equivalent to? Well, it's half an hour. So I would say I'm going to put a 1/2 on my number line. And I'm going to be interested in shading above it. And so in probability notation, I would want the probability that x, the amount of time I have to wait, is over a half hour. Now in both of these cases, I can easily figure out how to write this or calculate this probability. I'm going to do e to the negative value that I'm given, and then I'm going to use the appropriate lambda. Notice over here I'm using the value of 1. And so I get e to the negative 2. On this side, remember I should get the exact same thing ultimately. I'm going to get e to the negative 1/2, but I'm going to have to multiply by this lambda value because it also has hours, which is 4. But what's 4 times 1/2? Well, that's still 2. So both of these again are coming out to the same value. And if you were to go double check this on a calculator, you could see that I get the value of 0.1353. And of course I get the same thing on the other side. So again, when I do a problem, I don't have to pick any particular units. It's not like if I use the 15-minute units, or if I use hours, or if you converted everything into this problem into just singular minutes, you wouldn't ever be wrong. It's just a different way of tackling it. But if you understand how to move from multiple perspectives, you can save yourself a lot of time, because you might be able to pick the easiest possible approach. Let's take a look here at part B and try to see if we can do this again. What is the probability that Kyle has to wait over 10 minutes for the bus to arrive? Well, here's where you could start to see that maybe working in this 15-minute interval is going to be kind of annoying, right? Because like, if I wanted to work in this interval, I'd have to say 10 minutes is how much of a 15-minute chunk? Let's see, 10 minutes is how much of a 15-minute chunk? Well, I guess it'd be like 2/3. 10 is 2/3 of 15. So this can get a little bit messy. But if I ask, hey, 10 minutes is how much of an hour? That's not too bad. We might be able to more intuitively think about that and go, oh, it's just 1/6 of an hour. So notice I can divide my page and try this again. Over on this side, in the hours direction, things become pretty easy. So if x is being measured in hours, I can say that 10 is just 1/6 of an hour. And so I can set up everything I need over here very, very quickly. I want the probability that x is greater than 1/6. That's the same thing as e to the negative 1/6 times that value of 4. And if I crunch this out on a calculator, I get 0.5134. Notice I could work with things on the other side. That's not a problem. I just have x being measured still in these 15-minute chunks, and so I would need to be working with 2/3, because 10 minutes is 2/3 of 15. So here I would have probability that x is greater than 2/3. That would be e to the negative 2/3 times, remember, the value of 1. Notice again, this exponent and this exponent are going to end up identical, which means, of course, I'm going to end up with the exact same answer. So the units of time, again, that I choose to use are somewhat arbitrary. I can pick whatever makes the most sense to me. And so it's something that you want to make sure that you're careful of as you're working through your problems. In fact, I would suggest that you try using multiple units of time on the problems that you're working on in worksheets, just so you can get used to what's happening. And if you notice that when you look at my solutions, I'm using a different unit of time than yours, that's not a problem, right? We should still end up at the same solution as long as we've carefully stuck with those units all the way through. In the next video, we'll take a look at this interesting portion of this question, which is part C, and understand some cool properties about an exponential distribution.